design of pre-stressor concrete element, subject code 17 CV82 for 8th semester civil engineering students. First module, introduction and analysis of members. Today we discuss about section 3. In that, course outcome is analysis the stresses encountered in PSC elements during transfer and at working, presented by Naveen G.M. Here, basic principles of pre-stressing. To derive a general expression for PSC section by criteria are to evaluate the resultant longitudinal fiber stress in PSC section. We discuss here. In that, you take a cross section of any section. In that, this is the CG of a member, and also AB is the top fiber stress. Then this line represents the bottom fiber stress. In that, we have taken the distance, that is y, and we taken as E value. Here that is eccentricity, small e represents the eccentricity, and y is the distance represented from the top fiber. In y1 is the distance from top fiber, and y2 represents the distance from bottom fiber stress. Then coming to the before analysis this stress criteria, some analysis assumption will be made. In that, the analysis of stress development in PSC sections in bending, the following assumptions are made. In that, first one is assumption 1 is concrete is homogeneous and elastic material. Then this is same as in your RCC. What is homogeneous means? A mixture is homogeneous, it gets uniform in nature. And elastic material, already we know that concrete is elastic in nature. Then second assumption is within the range of working stress, both concrete and steel behave elastically, notwithstanding the small amount of creep which occurs in the both material under sustained loading. What is that means? In that, working stress means both concrete and steel in elastic, that is it regain its original property when after we take an external load on it. This is the meaning. We cannot withstand the small amount of creep also which occurs both the material. Then third assumption is a plane section before bending is assumed to remain plane even after bending. This is well known assumption made in concrete also, that is plane section remain same, which implies a linear strain distribution across the depth of the member. These are the some assumption made before to develop a equation for a stress. In that, let us take a pure stress due to axial effect, that is what is P represents the load applying, then A is the area of the section. In that, a pure stress in axial effect gives P by A, that is load by area. Then stress due to elasticity, that is elasticity means that is distance E, and that diagram you see. Then M by I into Y, that gives equal to M is equal to how much? P into load into eccentricity, that is moment due to eccentricity, I into Y, that is equal to PE by Z. Z means Y by I. Okay, section modulus, that is Z. Then stress due to dead load and live load, that is M by I into Y. That is M is the moment due to dead load and live load. That is equal to M by Z. What is Z is equal to section modulus. Then coming to, therefore, the stress developed along AB. The stress developed along AB means this top of the fiber. That AB is equal to P by A plus PE by Z plus M by Z. This is the equation to calculate the fiber stress developed in a top fiber. Similarly, where P is equal to P stressed force, E is equal to elasticity of pre-stressing force, then Y is equal to distance of long fiber lying along AB, then M is equal to bending moment across the section, I is equal to moment of inertia about Cg of bending. This is not a big E, this is small e. Then extreme fiber stresses in concrete PSC sections are analyzed in two stages of loading. Case A, that is at transfers of pre-stress on unloaded section or pre-stressing plus self-weight condition. Case B is at transfers of pre-stressed on loaded section or pre-stress plus self-weight plus live load. This is the condition, case A and case B. Let us discuss the case A, that at transfers of pre-stress on unloaded section or pre-stress plus self-weight condition, let Fu1 and Fu2 represents extreme fiber stress developed in cone at top and bottommost fiber at transfers of pre-stress. Further, P0 is the initial pre-stressing force applied to the tension steel, and MD is the girder moment or moment due to self-weight or moment due to dead load, whatever it may be. At this stage of loading, beam is assumed to carry a self-weight only. We assume here the beam is carrying only self-weight, not other loads. Then the top fiber stress developed in the member Fu1 is equal to P0 by A plus PEY1 by I plus MDY1 by I. What is this? Is due to axial stress, this is due to eccentric stress, this is due to movement. The stress developed due to movement. For this is dead load only. MD is the dead load only. Okay, the bottom fiber stress developed in the member, that is Fu2 is equal to P0 by A plus PEY2 divided by I plus MDY2 divided by I. Here this is for bottom, this is Y2 represent the bottom, here Y1 represent the top distance. Here same MD. Okay, only difference is Y1 and Y2. Here the equation are top and bottom. If AST is area of cross section in tensile steel and P0 is the initial pre-stressing force, the initial pre-stress Fs1 is equal to, or Fsi, we call it as Fsi is equal to, that is pre-stress at initial stage P0 by AST. That is, this is Fsi is the stress, this is the force, pre-stressing force. Okay, this is stress, this is force. This is area steel. Okay, ST, that is. Then case B, at working load condition or loaded condition, or whatever discuss here, this pre-stress plus sulfate plus live load condition. In that, let FL1 and FL2 represents the extreme fiber stresses developed in the concrete at top and bottom most fiber respectively. Here available effective pre-stressing force P, which will be less than initial pre-stressing force P naught because of losses. Okay, here ML is equal to bending moment due to superimposed load or live load. Therefore, total moment developed at live load ML is equal to MD total load. MT is equal to MD plus ML. At this stage of loading, it is assumed that the member carries both Gilder moment as well as moment due to superimposed load. Then come to the resultant stress developed in the top fiber. FL1 is equal to P by A plus PEY1 by I plus MIY1 divided by I. Here same as your previous equation, the only difference is P. On that we are using P naught, here P. This P is lesser than P naught, that is P naught is the initial pre-stressing force, P is the after the losses, we are getting this P value. The resultant stress developed in the bottom fiber stress FL2 is equal to P by A, that is stress due to pure axial, PEY2 divided by I, stress due to eccentricity, then MI, that is total load, we call it as MIR, MT, sometime MIR, MT, Y2 divided by I. That M, that is the moment due to total load, dead load plus live load. And also Y2 and Y are the bottom fiber stress, Y1 are the top fiber stress distance. Lastly, effective pre-stress available in the member, that is FSC is equal to P by AST. What is P? Is the after the loss in a pre-stressing force available in a member, we represent the P. And also FSC is the stress due to after the losses. Okay, then this AST is the area of cross section of a steel. Okay, this is how we can calculate the stresses in a member by stress criteria. Then loss ratio or loss factor, that is represented by nu. That what is loss factor or loss ratio means, it is defined as the ratio of effective pre-stressing force to initial pre-stressing force, or the ratio of effective pre-stress to initial pre-stress. Okay, that is nu is equal to P by P naught, that is P is equal to after the loss of pre-stressing force available, and P naught is the initial pre-stress force available. Then this is also represented by FSC divided by FSI, that is stress after the losses and stress in a initial state. We represented by FSC divided by FSI also, that is nu. Then note here, some notes is useful to what is nu. That is first point is nu is always lesser than 1. Why? Because this is the ratio, therefore it is always lesser than 1. Generally, loss of pre-stress varies from 15 to 20% Then new value 0.85 to zero point 0.8 only. Okay, what is 50 to 20% losses will be take place in pre-stressed, already we told in introduction part. Therefore new value is 0.85 to 0.8. Then if nothing is specified regarding the value of new, let us assume there is no loss of pre-stress, so that new is taken as 1 or P naught is equal to P. Okay, initial pre-stressing is equal to P anta tagabeku. There where we are no losses will be given means. Note number 2, the sign conversions. In that first one is compressive stress is treated as positive, so that tensile stress will be negative. Okay, here compression is taken as positive and tension will be taken as negative for sign convention. Any distance measured above neutral axis is positive, so that the distance below C central axis will be negative. Okay, above we are taken as a positive, below neutral axis we are taken as a negative. Sagging bending moment is positive, so that arcing moment is taken as negative. These are the sign convention we are taken throughout this PSC section. In that note number 3, that is self weight of the section equal to A into rho, that is area of cross section into density of concrete rho. Then where A is the total area of cross section and density of concrete is the rho. And note number 4, if nothing is specified regarding density of concrete, say that is 24 kilonewton per meter cube. The density of concrete, reinforced concrete is 24 kilonewton per meter cube is taken. If nothing is specified regarding this density. Note number 5, self weight of member will be UDL. Okay, always we are taken self weight of a member will be UDL. If nothing is specified regarding this. Moment due to self weight MD is equal to WL square by 8. If your UDL means, that is moment is calculated WL square by 8. In case of simply supported beam, both MD and ML, that is MD means moment due to dead load, moment due to live load, are sagging, that is MD you taken, bending moment due to sagging. In case of cantilever beam, bending moment due to self weight, MD is equal to WL square by 2. Okay, there's a cantilever other WL square by 2. In case of cantilever beam due to dead load and live load is arcing bending moment. We are taken arcing bending moment. Okay, here we are taken sagging bending moment for simply supported, arcing bending moment for cantilever beam. Then if 2-point load of equal magnitude, if there are equal space from their support, maximum bending moment due to dead load and to live load, ML is equal to W into A, that is load into some distance, measure a distance here, quarter distance. This is, we have taken a note before analysis on member. Then coming to the solution of problems. Before going to these problems, we carefully discuss about that note and read out that notes. Note will be very important to solve these problems. In that first problem, a rectangular concrete beam 100 mm wide into 250 mm deep, spanning over 8 meter is pre-stressed by a straight cable carrying an effective pre-stress force of 250 kilonewton, loaded at an eccentricity of 40 mm. The beam supports a load of 1.2 kilonewton per meter, that is UDL load. Calculate the resultant stress distribution for the central cross section of the beam. That second B, that is density of concrete is equal to taken as 24 kilonewton per meter cube. Then find the magnitude of pre-stress, that is eccentricity equal to 40 mm is given, which can balance the stresses due to dead load and live load at the central section of the beam. This is your problem given. Here for given data we draw the diagram of a beam or cross section of a beam. What is given here? 100 mm wide. We draw a 100 mm horizontally, that is wide. 250 mm deep, 250 mm deep beam will be, rectangular section will be shown here. In the 8 meter span, if you have taken a span of this cross section is 8 meter here. Straight cable, this represents the straight cable with a force of how much? 250 kilonewton. PS value is 250 kilonewton at an eccentricity, that is equal to 40 mm from the centroidal axis. And also how to calculate the y1, y2 for this section is, that is y1 is 125 mm, y2 is equal to 125 mm. Then another data is given here is the beam is supported a load of 1.2 kilonewton per meter UDL. Okay, in that we can calculate the what is the movement due to this load. Okay, at that particular case, for this we are solution of this problem will be discussed here. That first step is calculate the area of cross section, that is equal to 100 into 250 equal to 2.5 into 10 raised to 4 mm square. Okay, the area of cross section will be calculated here. B into D. Here y1 is equal to plus 125 mm and y2 is equal to minus 125 mm. This is for top positive, bottom that is negative. Eccentricity of CG of tension steel E is equal to, that is minus, that is bottom representing here bottom, minus 40 mm. Then Mi, the moment of inertia about centroidal axis, I is equal to BD cube by 12 for rectangular section, that is 100 into 250 meter cube by 12, that is I is equal to 1.3 to 10 raised to 8 mm to the power of 4, that is I value. Then self weight of the section is equal to 0.25 into 0.1, that is 100 into 125 or 250 into 24. Okay, that is converted in meter, that is 0.6 kilonewton per meter. This convert 0.6 kilonewton per meter to Newton, means 600 Newton per meter. Therefore, maximum girdle moment at centroidal section MD is equal to WL square by 8, that is W is equal to 600 into 8 square by 8, that is 600 into 8 square divided by 8 means 4.8 into 10 raised to 6 Newton per mm square. This is the moment due to dead load. Okay, only for dead load, that is self weight will be calculated by using this formula. Then given live load is equal to 1.2 kilonewton per meter. The maximum bending moment due to superimposed load at centroidal section, that is ML is equal to WL square by 8. Okay, here we taken a UDL that is 1.2. Why you are taken is UDL here means is given 1.2 kilonewton per meter. Okay, 1.2 into 10 raised to 3 into 8 square, that is length of the beam, by 8 into 1000 gives equal to 9.6 into 10 raised to 6 Newton per mm square. This is due to moment due to live load. This is moment due to dead load. Then the total moment at centroidal section, that is MT is equal to MD plus ML, that is equal to 4.8. This is 4.8 plus 9.6 gives 40.4 into 10 raised to 6 Newton per mm square. Okay, this is the total moment at center section. Then here effective pressure force equal to 250 kilonewton is given. Here 250 equal to 2.5 into 10 raised to 5 Newton. We are converting for Newton. Then the first to evaluate the resultant stress distribution for the central section of the beam. Note, since effective pressure force is given and loss ratio nu not given, okay, stress extreme resultant fiber stress to extreme fiber stress at working load. Okay, here there is no loss factor is given, therefore nu is assumed as 1. Let FL1 and FL2 represents resultant extreme fiber stress in concrete at top and bottom most fiber at central section respectively. The top fiber stress FL1 is equal to P by A plus PEY1 by I plus MTY1 divided by I. This is due to total load acting on a section, total moment acting on a section. FL1 equal to 2.5, that is pressure force into 10 raised to 5 divided by area of cross section upon member 2.5 into 10 into 8, and P is equal to 2 into 2.5 into 10 raised to 5 into eccentricity minus 40 into minus 125, that is top fiber stress, that is we taken here, that is positive. Okay, here we taken this is positive not negative, divided by 1.3 into 10 raised to 8 plus 14.4 into 10 raised to 6 into 125 divided by 1.3 into 10 raised to 8. That FL1 gives the value 14.23 Newton per mm square. This is positive sign indicates the compression at the top. That is positive sign indicates the compressive stress at the top fiber. Then coming to the next bottom fiber stress, FL2 is equal to P by A plus PEY2 divided by I plus MTY2 divided by I equal to 2.5 into 10 raised to 5 divided by 2.5 into 10 raised to 8 plus 2.5 into 10 raised to 5 into minus 40 into minus 125. This is represent the bottom distance divided by I value 1.3 into 10 raised to 8 plus 14.4 into 10 raised to 6 into minus 125 divided by 1.3 into 10 raised to 8. That gives FL2 is equal to 5.77 Newton per mm square. This is positive, but here we are strictly speaking answer must be negative. why this positive comes means a section is too large for dead load and live load. Okay, here strictly speaking negative, but we are getting was positive because we are get section is too large. To evaluate the magnitude of pre-stressing force which can balance the stresses due to dead load and live load at bottom fiber of central section. This is the second point that we are getting that one. Then note, to nullify the, to evaluate the magnitude of pre-stressing force, that is E value na, we can find out the P value. In that, to nullify the effect of dead load plus live load means tensile stress to the taken 0. Since it is for bottom fiber, FL2 is equal to 0. Okay, that is bottom fiber stress FL2 represent the 0 here. Okay, in that is 0 is equal to P by A plus PEY2 divided by I plus MTY2 divided by I. In that is 0 is equal to P by 2.5 into 10 raised to 4 plus P into minus 40 into minus 125 divided by 1.3 into 8, that is I value. Here that is negative, that is why, because bottom fiber stress plus 14.4 into 10 raised to 6 into minus 125 divided by 1.3 into 10 raised to 8. That represent gives solving this equation, simultaneous equation, that is P is equal to 1.764 in 10 raised to 3 Newton it comes. Here for kilonewton, this is 1.764 kilonewton we are getting here. These are the some references we taken for studying this, preparing these slides. Here that is some code book also we are getting here. Thank you for listening this session. If any queries, please ask free. We can answering that questions. If any doubts, please ask here for this particular session.